So in this video we're just going to do some more examples of linear systems that are homogeneous, constant coefficient. Okay, so you see an example, dx dt equals 5x minus 9y, dy dt equals a half x minus a half y, and we have initial conditions. So our approach is to find two, hopefully there will be two, straight line solutions, and then form the general solution out of that, and then apply our initial conditions. So we need eigenvalues and eigenvectors. Okay, so we compute the determinant of this matrix. So here I've taken the four coefficients, 5, negative 9, half, negative a half, put minus lambdas on the main diagonal, and I'm going to take the determinant of that. That turns out to be this expression, and I want to set that equal to 0. Now the problem is this is going to be a quadratic in lambda. I have to do some algebra. It's not factored because of the plus 9 halves. But when you multiply this all out, and I'll shortcut to after you multiply it out and collect terms, you get lambda squared minus 9 halves lambda plus 2 equals 0. And you can use the quadratic formula, or actually this can be factored. I can multiply through by 2 to get rid of the fraction because we're not used to factoring with fractions. And it factors as 2 lambda minus 1 lambda minus 4 equals 0. You could also, like I said, use quadratic formula at this level. It'll be fine. And in fact, the square roots will be doable, and you'll get clean numbers. And the clean numbers end up being 1/2 and 4. Okay, so next, after finding the two eigenvalues, and we did get 2, so that means this is going to be doable based on what we've learned so far. We need to find the eigenvectors. All right, so for lambda equals 1/2, I put 1/2 into this matrix. That gives me 9 halves, negative 9, 1/2, negative 1. And I'm looking for a vector that this kills, a vector that's in the kernel of that matrix. What always happens in this case is that the first row and the second row should be multiples of each other, and you see they are. If that doesn't happen in a 2 by 2 situation, then you've done your eigenvalues wrong, because that always should happen. And so they're really just repeats. Saying 9 halves x minus 9y equals 0 is the same as saying 1/2 x minus 1y equals 0. The first equation is just 9 times the second equation. So I'll just work off of the second one just because it doesn't have that 9 in it. I'll say 1/2 x minus y equals 0. Right, so I can multiply through by 2 if I want. I don't have to, but x minus 2y equals 0, so x equals 2y. So I could pick like a 2 and a 1, and that'll work. And that'll be an eigenvector for 1/2. All right, next I go to lambda equals 4. I put 4 in for lambda up here. That gives me 1, negative 9, 1/2, minus 9 halves. Okay, and again you see that the top row is 2 times the bottom row. I'll go with the top row because it doesn't have fractions. X minus 9y equals 0. So x has to be 9 times y. So 9 and 1. All right, so my general solution then is going to be C1 times the solution I get from the first calculation. So that's 2, 1, e to the 1/2 t. And then plus C2 times the second one, 9, 1, e to the 4t. So this on its own was a straight line solution. This on its own is a straight line solution. This one has initial condition 2 and 1. This one has initial condition 9 and 1. But we want to be able to get any initial conditions, so we put them together like this, and the linearity principle says that's okay. All right. now we're ready to apply our initial conditions. And our initial conditions were -2 and 0. So -2 and 0 equals C1, 2, 1. And I'm putting 0 in for time, so the exponentials become 1, plus C2, 9 and 1. Okay, so you can write that out. That's, -2 equals 2C1 plus 9C2, and 0 equals C1 plus C2. And you can solve that however. You can RF it or do high school algebra on it. I think that you will get C1 equals 2/7 and C2 equals -2/7. So our final solution then is that y equals 2/7, 2, 1, e to the 1/2 t minus 2/7, 9, 1 e to the 4t. And that's our answer. Here's a second example. In this example, we're going to do a second-order differential equation. It's going to be an object attached to a spring. Now, we already know how to do this more directly, but we have talked about how second-order differential equations can be turned into a first-order system with two equations. And so I just want to show you that. Yeah, it's just an alternative way to do this one. So we have a 1 kilogram object attached to a spring with a spring constant of 28. And there is some damping. There's a friction or drag, and B is 11. It's pretty strong. And we push it in 3 units and then let it go. So that right there is giving us initial condition. And the question is, where is it after 2 seconds and after 5 seconds? Okay, that's fine. Let's set up the differential equation and solve it, and then we'll be able to plug in 2 and 5. Okay, so the second order differential equation for a mass on a spring looked like this. We have no forcing, so it is homogeneous. And with our particular numbers, we have 3 for the mass. 1 for the mass. Actually, I'm going to make this be 3. Yeah. No, sorry. I'll leave it at 1. Plus 11 dy dt plus 28y equals 0. Okay, now the way we make this into a system is we let v equal dy dt. V for velocity, because it is, right? If y is where the object is, then the derivative is the velocity. And that's actually our first equation. And then we turn our differential equation, that'll give us our second one. So the second derivative of y will be the first derivative of v, and then dy dt is just v, and 28y equals 0. Okay, so now just to rewrite that more standard way, dy dt equals v, and dv dt equals 28y plus 11v. Negative. Okay, so our matrix here is 0 and 1, -28 and -11. Notice I was careful. If I'm doing dy dt and dv dt, then I have to do y and then v. I have to be consistent in my ordering of the two quantities. All right, so now we do eigenvalues. So we do negative lambda, 1, -28, minus lambda minus 11 minus lambda, and we take the determinant of that. There it is, and we set it equal to 0. And when we work this out, we get a lambda squared, we get plus 11 lambda, we get plus 28 equals 0. And let me just point out that, and this will always happen, that we get a characteristic equation, lambda squared, we get 1, 11, and 28, right, which were the original m, b, and k. And so we're solving the same characteristic equation that we would normally have solved if we did it the old way, just not changing it into a system. We would have written down this equation. So you see that in the end it kind of matches what we were doing before, and it's not a completely different type of approach, although there will be differences as we continue. All right, so that I'm going to solve, let's see, what would that be? That'll be 4 and 7 work, right? So lambda plus 4, lambda plus 7 equals 0, so lambda is negative 4 and negative 7. All right, for lambda equals negative 4, we have a matrix that will be 4, 1, negative 28, negative 7. What vector is going to be killed by that matrix? Again, you see that the second row is just a multiple of the first row, so I can just use one row because the other one's redundant. So I can do the first one, 4x plus y equals 0. Y would be negative 4x. So if I make x be 1, y would have to be negative 4. Remember, I'm picking, I could also do 2 and negative 8. That also works here. Or 3 and negative 12. I'm just picking a convenient pair of numbers that work in this equation. Because remember, eigenvectors, it's really any multiple, all multiples of any one eigenvector are also eigenvectors. Okay, lambda equals negative 7. That'll give us positive 7, positive 1, negative 28, negative 4. So 7x plus y equals 0, or y is negative 7x. So I can go with a 1 and a negative 7. Okay, which gives me now a solution of C1, 1 negative 4, e to the minus 4t, plus C2, 1 negative 7, e to the negative 7t. All right. In terms of initial conditions, actually, before I do the initial condition, let me just point something out. Right here, so our little y is, if I just read off the top, right, that'll be C1 e to the minus 4t plus C2 e to the minus 7t, which looks a lot like, and is, what we, the type of thing we got for in an overdamped situation, the old way of doing these mass on spring problems. So that should look pretty familiar. No sines or cosines because we got two real solutions, and there was just two exponentials with constants in front. One nice thing is that this automatically gives us the v, the derivative. So we see that that's minus 4c1 e to the minus 4t minus 7c2 e to the minus 7t. There we go. So that comes for free, although that wouldn't have been hard. That's just the derivative of y. You can see that. Okay. Now, initial condition, again, it was we push it in 3 units and let go. So I guess it's starting at a negative 3. And we're just letting it go, so we're giving it no velocity. Okay, so that's how our initial condition looks in vector form. So we'll have negative 3, 0 equals C1, 1, negative 4, plus C2, 1, negative 7. Okay, and we can solve that, and again, I'll just fast forward through the algebra here, RFing it or whatever, and we get C1 equals negative 7, C2 equals 4. All right, giving us a final solution of y equals negative 7, vector 1, negative 4, e to the minus 4t, plus 4, 1, negative 7, e to the minus 7t. And that's our answer. And again, the top is going to be the position, that's going to be y. So little y will be negative 7 e to the minus 4t plus 4 e to the minus 7t. And the velocity will be the bottom row, 28 e to the minus 4t minus 28 e to the minus 7t. We see they're both negative exponentials, both die out over time. This is typical overdamped situation. And then finally, we can answer the questions, where is it after 2 seconds, where it is after 5 seconds. So we just want y of 2 and y of 5. And you just plug it into your formula for y, and that will give us, in one case, it's negative 0.00234. So it's died out a lot just after 2 seconds. It's very close to 0. It's a slightly on the negative side. And for 5, gosh, that's going to be even closer to 0. Yeah, that's really small. It's negative 1.44 times 10 to the minus 8. Okay, so very small. All right, so here have been 2 examples of the eigenvalue-eigenvector method for solving systems. In the second one, we actually did it on a second order, that we convert it to a system. And what still needs to be discussed is what you do when you don't get 2 real eigenvalues and their corresponding eigenvectors. Then our approach breaks down, but we can fix it, we can tweak it, and get it to work still. So that would be the next thing on our docket to take care of.